All right, let's get started. So, over the course of the semester, we started really from a far-field point of view on the airplane and started zooming in gradually, right? So we zoomed in into the span of the airplane and used vortices to approximate the flow around an airplane. And then we zoomed more into the airfoil, into a cross-section of the wing, and looked at potential flow around an airfoil, right? And we studied thin airfoil theory and things like that. And in the viscous flow section, we started to zoom in even further into the boundary layer and started looking at the detailed behavior of boundary layers, like across the very thin layer. And today we're going to reverse the process, now start to zoom out a little bit. Since we have now looked at the detailed behavior of the boundary layer, right, how the thicknesses, the skin friction on boundary layers work, now we start to zoom out and look at the effect of the boundary layer on performance, right now on airfoil, drag, and lift. So just first of a review of because we are going to be touching both turbulent and laminar boundary layers, we are first going to look at how a turbulent boundary layer behaves, especially what is the effect of turbulence on flows in general. So last lecture we looked at a uniform shear flow, right, sandwiched between two plates, one stationary, one moving, and we looked at if there is no turbulence, the flow is going to be a straight line. The velocity profile is going to be a straight line. Velocity is going to be linear with respect to the distance to the wall. And when we have more and more turbulence, the region far away from the wall is going to have a slower slope, right? It's going to change more gently compared to the region very close to the wall. Okay, so that's going to be a universal feature of turbulent shear layers. Closer to the wall, there is less turbulence, and as a result, there is more velocity gradient. And similarly, we looked at this flow between also two walls, but both walls are stationary, and the flow is driven by a pressure gradient. And we also used the Desmos to demo to look at what is going to be the velocity profile in that case. And we reached a similar conclusion in the sense that when the flow is laminar, the flow is profile is parabolic, and when the flow has more and more turbulence, there is less and less velocity gradient in the middle of the channel, and more velocity gradient near the wall, right? Or the vorticity in this case is more concentrated closer to the wall, and the less in the middle of the channel. It's going to be the same for turbulent boundary layers. Okay, actually part of the homework due this week is to look at a very similar case. So instead of a two-dimensional flow over a channel, you have to look at a three-dimensional flow over a circular, a cylindrical pipe, right? And I would say the analysis is similarly simple, right? Except the calculus is different. And the result is going to be as simple as this one. So yeah, if you have questions, I'll be answering questions in office hour after the lecture today. All right. So one question we have is now looking at boundary layers, can we use the same principle to answer questions like this, right? So we have a bunch of different colored profiles. The question is which of them would represent a turbulent boundary layer on the flat plate? Which of them would represent laminar boundary layers on the flat plate? Anybody can just use what we looked at the last two slides and distinguish between a turbulent and a laminar boundary layer. Yeah, let's look at the profiles and tell me which one is turbulent, which one is laminar. Yeah?
Dark blue, light blue, and brown, black, or turbulent. And the other three that are like shallower than that.
That's exactly right. How did you make the distinction?
So we saw earlier the laminar boundary layers are more likely to have like that kind of linear gradient, like very consistent
That's right. So in laminar boundary layers, in the green one, the magenta one, and the red one, they are laminar boundary layers. And if you look at the vorticity distribution, right, in this case, we have parallel shear. So the vorticity is proportional to the derivative, to the gradient of velocity with respect to y, right? The vorticity is more uniformly distributed across the boundary layer. Of course, as you get closer to the edge of the boundary layer, the vorticity decays all the way to 0, right? But if you look at the green line, for example, going from 0 to 1, the vorticity is pretty uniformly distributed. But in the turbulent boundary layer, it is never the case, right? Except for in the extremely thin layer close to the wall, we call a laminar sublayer. Except for that extremely thin layer, the vorticity is never uniformly distributed. The vorticity is always going to be smaller and smaller as you get further and further away from the wall, right? And it is extremely concentrated in the a very small region near the wall. All right. Okay. Any questions on this? And both laminar and turbulent boundary can be of any thickness, right? So you cannot use the thickness to distinguish between them. All right. Okay. So now the important thing we want to discuss is how much drag does boundary layers cause. Okay. So we start from skin friction drag. So the drag due to the accumulation, the integration of shear stress on the surface. So we start this by looking at a flat plate, right? And we know on a flat plate, the boundary layer is the Blasius boundary layer, and it is of a fixed shape, right? No matter how thick the boundary layer grows, the shape is the same. The only difference is when you change the velocity, this scale changes. And when the boundary layer grows thicker, this scale changes. Right? So if you normalize the x-axis by the velocity and normalize the y-axis by a square root of velocity divided by viscosity, you get exactly the same profile. Okay, and that we're going to see at the next slide for turbulent boundary layers. It is no longer the case. Okay, so for laminar boundary layers, because we know the profile is the same, right? So the derivative at the origin is exactly the same, and that is allows us to calculate the shear stress, right? So we know the shear stress, tau, is going to be the viscosity times du dy at y equal to 0 at the wall, right? So it is going to be a constant, whatever this slope is, right? It is going to be that constant of this slope on the picture times u infinity, so it's called the v infinity in this case, v infinity divided by a, let's just use the momentum thickness, right? So we know the momentum thickness in this case, I think in the last lecture we did the calculation, the momentum thickness is something 0.3 something, right? Times, the momentum thickness is integrated to be, I think 0.3 something in this scale. So we know that tau is proportional to actually times mu, right? A velocity divided by length times mu. So that's how much skin friction we have. All right. And through a momentum analysis, so remember the control volume we did, right? We did a control volume that follows a streamline, and we calculated how much momentum defect, right? How much loss of momentum does this part has relative to x equal to 0, right? And figured out the momentum loss is actually exactly equal to rho, in this case v infinity square, times the displacement thickness. So that's how much momentum loss we have due to the boundary layer, right? Due to the accumulated skin friction per span, right? Okay. So what that means is that if we take a derivative of this momentum loss, it is going to be exactly equal to the skin friction, right? So if I write it more carefully, it is the d of this, the change in the momentum defect or change of momentum is equal to the tau times dx, right? Both left hand side and right hand side should be multiplied by the span, right? If we want to get a unit of actually force on both sides. But of course the span cancels out. So what we ended up having is d, let me write this out, rho u infinity d theta dx is equal to tau, which is proportional to v infinity over theta times mu, right? Okay. So now if we normalize both sides by rho v infinity square, what we get is that d theta over dx is going to be proportional to mu over rho. Sorry. Yeah, thank you. Rho, mu over rho v infinity, and there is a theta, right? Agreed? Okay, this allowed us to, okay, so let's actually non-dimensionalize both x and theta, right? So let's go to the non-dimensional form. And if you look at this part, this is 1 over re theta, right? Reynolds-Steinberg with respect to theta. Okay, and you also realize Rex, Reynolds-Steinberg with respect to x, is rho v infinity x divided by mu, right? It's the same thing. So on the left-hand side, you can basically write the left-hand side in terms of d re theta, d rex, right? Proportional to 1 over re theta. So simple, right? There is basically a constant, the proportional is basically a constant, right? Times. Now what that means is that d, if you multiply both sides by re theta, d re theta squared is going to be proportional to d rex, right? It's basically multiplying re theta onto this and multiply re theta onto there, right? And re theta times d re theta is half of d re theta squared. So because we are writing proportional anyway, just re theta, right? So this is the case, which means that re theta is proportional to square root of rex. All right, agreed? So that's what happens for laminar boundary layers. And then now let's plug this back into the into tau, right? So tau is going to be well, let me just write it down. Tau is equal to, we actually divided by, okay, so tau is equal to rho v infinity squared, okay, times 1 over re theta, right? Okay, so what that means is that the tau will be proportional to rho v infinity squared times 1 over square root of rex, right? Or the skin friction coefficient is defined as tau normalized by half of rho v infinity squared is going to be proportional to 1 over square root of rex. Okay, so that's the derivation of how the skin friction changes as a function of Reynolds-Steinberg with respect to x in laminar boundary layers. And if you work out the exact coefficients, like from the Blasier's boundary layer solution, that's the coefficient, right? Skin friction coefficient is equal to about 0.66 divided by square root of rex. So the typical plot you see is that CF versus rex is going to be following a curve that's kind of like 1 over square root, right? Okay, didn't draw it very well here, but like it's going to go down slower than like a 1 over x relationship. All right. Any questions on this? Okay, now if the skin friction and especially the shear stress goes down like 1 over square root of x, how about the drag? How about the total drag, which is going to be equal to, of course, the span times the integral from 0 to x, tau times dx, right? Okay, so here what we get is if we plug this in, of course we have b times rho v infinity squared right now, and then we have going from 0 to x of 1 over rex, and 1 over rex can be written 1 over square root of rex, so that can be written as square root of x and multiplied by square root of rho v infinity and square root of mu, right, dx. All right, so if we integrate this, right, integrating 1 over square root of x, well, actually this is proportional because we have this proportionality constant over here. Okay, so if you integrate this, what we get is actually the integrating of 1 over square root of x is equal to square root of x, right? There is a coefficient of 2 that comes out. So because we are writing proportional, it doesn't matter anyway. What we have is going to be square root of mu, square root of rho v infinity times square root of x. All right. Okay, and now let's what do we have here? Okay, so now the important thing is for us to figure out what is the drag coefficient. So if we write down the drag coefficient, CD is going to be equal to the drag divided by half of rho v infinity squared, and then divided by area. The area is going to be b times x, right? So yeah, let me actually write the length of the integral, not using x, but using the length of the using the length of the plate. So integrating from 0 to L, and as a result, this is L, right? So the area of the plate is B times L. So if we pull all of these out, then what we have is going to be, so if we plug the drag into this equation, we're going to see B cancels out, rho infinity cancels out, and the L cancels out partly. What you get is actually going to be proportional to square root of mu divided by rho v infinity L, right? Which is equal to 1 over square root of RE L. So the drag on the flat plate also follows the trend of so the skin friction drag coefficient also follows 1 over square root trend if we non-dimensionalize the length of the plate, also in terms of Reynolds number. All right. Okay, so this is for laminar boundary layer. For turbulent boundary layer, the relation is a little bit different. So for turbulent boundary layer, right, so we have a laminar boundary layer and transition into turbulent. The turbulent boundary layer, again, like has a gradient much higher near the wall, right? And exactly how much higher is the gradient near the wall compared to the rest of the boundary layer actually depends on the Reynolds number. So the du dy at y equal to 0 is not just proportional to V infinity divided by theta as in the laminar boundary layer case, but it is going to be V infinity divided by a small fraction of theta. Okay, and how exactly that small fraction is actually again depends on the Reynolds number. The higher the Reynolds number is, the bigger, the smaller the fraction of theta is, right? So theta is roughly overall height of the boundary layer, but if you extrapolate this slope, right, to here, you're gonna see this is gonna be a small fraction of the thickness, and the higher the Reynolds number is, the smaller the fraction is. So this is actually multiplied by Re theta to some negative power, right? And that negative power, like based on data, is roughly 5/6. So which means that as the Reynolds number based on the thickness grows, the derivative, the derivative here is not that sensitive, right? So as my theta grows larger and larger, the gradient at y equal to 0 does grow a little bit, but the growth is not going to be, so sorry, the derivative actually decays, but it doesn't decay like 1 over the thickness. It decays at 1 over a small power of the thickness. Yes?
Small negative power, like it's in the denominator and the power of the Reynolds number is negative, or?
You mean this power is negative, right?
Okay, yeah, that's correct.
Yeah, this power is negative because the higher the Reynolds number is, right, the smaller, the thinner the laminar sublayer is compared to the overall thickness. So basically, the larger the Reynolds number is, the steeper the slope is if you look at the profile at the scale of the overall thickness. All right. Okay. I think I can skip the derivation, but like you can follow exactly the same analysis I did in the last page, right? So the primary difference is that let me actually do a little bit derivation, but skip most of the stuff. So tau would be proportional to mu times du dy, right? And if you plug in the skin friction coefficient, so Cf, which is going to be tau over rho V infinity squared, is going to be proportional to 1 over Re theta, not to the so previously Cf is actually the skin friction coefficient, right? Didn't do it here, but tau divided by rho infinity square is 1 over Re theta, right? In this case, it's 1 over Re theta to a small power. All right, and when you write down the equation d theta when you write down dre theta drex, so instead of being proportional to 1 over Re theta, it is going to be proportional to 1 over Re theta to a small power. As a result of that, Re theta is going to be proportional to Rex, not to the half power, but to a power of 6/7. So that result already tells us something pretty remarkable about turbulent boundary layers. So if you look at this picture, right? So here in the beginning, in this laminar portion, the theta or the thickness grows like x to the half power, like a square root relationship. But now in the turbulent region, theta no longer grows at x to the half power, but x to the 6/7 power. And 6/7 power is almost the power of 1, right? So that means as I go downstream, by another factor of so if I look at a very thin airfoil, right, almost a zero camber airfoil, I look at net span versus looking at the trailing edge. If if the boundary layer is laminar, then at the trailing edge, the boundary layer thickness is square root of 2 times the thickness at the midchord. But if the boundary layer is turbulent, then the thickness at the trailing edge is going to be almost twice as the boundary layer thickness at the midchord, right? Even without any pressure gradient. Yes?
Two questions. The first one, where do you get the constant, the proportionality constant for
So where do I get the proportionality constant for this one?
Yeah, that one.
Yes, I didn't follow the math here, but the constant would also first of all go into here, right? The du dy being a constant times v infinity over theta, and that constant is exactly from the Blasius solution. Right?
Oh.
There is no analytic solution to the Blasius solution. You have to solve it and measure the slope of the Blasius solution at y equal to 0. So
Right.
that's going to, and also you have to divide by theta, which is an integration over the Blasius solution. The ratio of the slope and the integral is going to get you the constant over here, and that propagates all the way to the end of the analysis to this number.
Right. My second question is exactly that. Like, can you give a little more insight about why? Or I guess I didn't get why the shear stress equals v infinity by theta.
So the shear stress.
The first equation.
Oh, the first equation.
Yeah.
Right. So v infinity by theta times a constant is going to get you the slope of the velocity at 0, right? So v infinity by theta is just a scaling constant. So if you make v infinity twice as large, right? This picture is not going to change, right? It's just that the x-axis is normalized by v infinity. So which means if you plot the x-axis not with u by u infinity, but u itself, then changing u infinity by a factor of 2 is just going to scale this curve to the right by a factor of 2, right? That increases the slope at y equal to 0 by a factor of 2. On the other hand, the y-axis, right, is non-dimensionalized. But if you actually increase the thickness by a factor of 2, right, increase theta by a factor of 2. So if you, instead of plotting the non-dimensional y, you plot the actual y-axis, increasing theta by a factor of 2, it just stretches this picture upward by a factor of 2, which decreases the gradient by a factor of 2. Right, so essentially v infinity over theta is a scale of the dimensional version of the picture that gives you the dimensional slope of du dy at y equal to 0.
Right. So that equation is assuming that that graph is a straight line for the most part.
Yeah, the graph is basically, so this is assuming this graph is universal. It doesn't have to be actually a straight line, right? So it basically assumes this graph is going to be the same graph no matter what v infinity is, no matter what theta is.
Right.
Yeah.
Yeah, that makes sense.
Okay.
Oh, it says y equals 0. That's what I did.
Yeah, at y equal to 0.
Yeah.
So tau is always y equal to 0. Yeah.
And my third question is, where do you get the 5/6?
The 5/6 is just from empirical data, right? So the 5/6, there is no analytical solution. I mean, turbulence is still at this day like something that we don't have any analytical solutions for turbulent flows. So all of these constants, they come from two sources. One is from experiments, and two is direct numerical simulations. So we basically have to solve the Navier-Stokes equation using very fine grid, using a very accurate numerical scheme, and resolving all the unsteady motions and average the solution to get the data like that, right? So that's really the two main sources of our data with turbulent, any kind of turbulent flows. All right. Okay, so. Right, so basically this derivation gets us how the thickness evolves. It also gets us when we plug in the thickness, right, into the skin friction. So if Re theta is Rex to the 6/7 power, then skin friction coefficient is Rex to the about 1/7 power, right? So, so these two conclusions, right? One is how the thickness of a turbulent boundary layer grows. It grows almost linearly. It's slightly slower than linearly, but almost linearly. And the two is how does the skin friction coefficient decrease as X evolves. Again, the skin friction coefficient decreases as X increases, but decreases at a very slow rate, right? So these are the two main conclusions on turbulent boundary layers. So normally when you see a skin friction coefficient versus X during a boundary layer that is first laminar and then turbulent, what you see is that initially you have this 1 over square root of, let me see, this is REX. 1 over square root of REX behavior initially, and then at some point you have flow transition. And then afterwards the skin friction decays at a very slow rate. So that's the normal skin friction coefficient curve you see on the laminar then turbulent boundary layers. All right. Okay. Questions? All right. So this is one slide on what promotes flow transition. This is not going to be tested in this class, right? I mean, flow transition is actually even more complicated subject than turbulent boundary layers. So I'm just going to give you a very quick overview of what is the current best model of flow transition. So flow transition is caused by tiny perturbations that goes into the laminar boundary layer. And these tiny perturbations for certain type of boundary layer profiles and thicknesses, these perturbations are unstable, which means as these perturbations advance downstream, the perturbations are going to become larger and larger perturbations. And flow transition occurs when these perturbations becomes as large of a magnitude as the velocity, as the steady state velocities in the boundary layer itself. Right, that's when the boundary layer becomes turbulent. And there are the two difficult things is one is to predict how fast these instabilities would grow, but the even more difficult thing is to figure out how much of these small perturbations are there initially, right, in the boundary layer, because these perturbations can be very small, right? They can be in a very quiet flow. It can be like 10 to the -7, 10 to the -8, right, compared to the free stream velocities, right? Really, really tiny perturbations. So when you see like people who are trying to maintain laminar flow are very, very careful with even if a box sticks to the leading edge, there is no way you're gonna get the same laminar flow you get before, just because of the small perturbations introduced by the bug or like a spray of salt water or something like that, right? Okay, so this picture basically shows you the two most important things that affects transition. One is the Reynolds-Steinberg. So this picture tells you the boundary between so below this red curve, the perturbations, any perturbation you put into the boundary area would not grow in magnitude. Above this red curve, there are certain small perturbations you put into the boundary layer that would grow exponentially, right? So this really tells you the curve, the separation between so underneath the curve, it is impossible to have transition, and above the curve, depends on what perturbations you have, right? You may have transition. All right. So it tells you the most of two important things. One is RE theta. Okay. So if the boundary layer is thicker, right? Thicker in a non-dimensional sense, right? That's why we have RE theta. Okay. It is more likely to transition. And two is the shape factor H. Again, that's the ratio between a displacement thickness and the momentum thickness. So for a higher ratio, it's more likely to transition. Okay, and we're going to see that a little bit later. So here we are plotting several different boundary layer profiles. And of course, we have analyzed, right? In the lecture, we talked about how a boundary layer is affected by pressure gradient. So can somebody look at the boundary layer profiles and tell me which ones are more likely to be subject to a favorable pressure gradient, which one is more likely to be subject to an adverse pressure gradient? So if you don't remember, we should we can take a look at take a look at the decimals we did some time ago, right? So we can change the pressure gradient. So initially the boundary layer profile is the purple one, right? As we make it more and more favorable, the profile becomes more like this. And as we make it less and less favorable, and now to adverse pressure gradient, the boundary layer becomes something like this, right? So if you can kind of connect the center of these red lines to visualize what the actual boundary layer would be like, and then correlate this with what we see the new slide, you might be able to figure out which one is adverse, which one is favorable pressure gradient. Anybody wants to take a guess? Yeah?
I would guess the magenta is favorable and the black is not favorable.
Yes. So in this case, one way actually to look at it is to look at the curvature of the velocity at the wall, right? So any favorable pressure gradient is going to have a curvature like the magenta line. So the curvature is going like this. Any adverse pressure gradient is going to have a curvature like the blue and black lines going like this. Okay, so this is actually usually the most straightforward way of telling which one is favorable, which one is adverse. So now with the knowledge that the magenta one is most favorable pressure gradient, the black is most adverse pressure gradient, which one has a higher H, higher shape factor? All right, so H is equal to the ratio between the displacement and momentum thickness, right? So the displacement thickness is 1 minus u over u infinity integrated. The momentum thickness is u over u infinity times 1 minus u over u infinity integrated, right? So basically it's looking at if the shape factor would be high if this value is going to be small, right, for most of the deficit, and the shape factor would be low if u over u infinity is close to 1, right, over most of the deficit. Right, and again, we can go back to this decimals demo, and it actually reports what is the shape factor on the different pressure gradients. So on the favorable pressure gradients, somehow did I report H somewhere? Yeah, I think I did. It's just overwhelmed by. Yeah, just go to a go to a web page. Right, so H is actually reported over here. So as I make it one more favorable, H is 1.2 something. As I make it decrease, H becomes 1.7, 1.8, 2, and and 3. So basically, the more adverse pressure gradient I have, the bigger my shape factor is, right? If you look at this. So if we go back to our notebook, the black one is going to have the highest shape factor, and the magenta ones is going to have a low shape factor. So which means the black boundary layer profiles on the adverse pressure gradient is more easy to transition, right, than the favorable pressure gradient. Yes?
Don't you need at least 2 different points of velocity to really know the pressure gradient, or how are you determining the pressure gradient just from one for the velocity at one point?
Right. So I would need the velocity outside of the boundary layer at 2 different x locations to know the pressure gradient. That's correct. But I can also know what the pressure gradient is, right? Or at least the average pressure gradient is in a small region upstream of this point, if I know the boundary layer profile, right? Which means how the boundary layer, how the velocity changes across the thickness of the boundary layer. This is because the boundary layer is a symptom of pressure gradient. If I have a favorable pressure gradient in a region before this x location, the boundary layer at that x location would look more like the magenta case, right? If I have a pressure gradient in a small region upstream of the x location that's adverse, the boundary layer would more look like blue or black.
That is with respect to like Watt's formula, or what, or like how do, I think I'm not getting, how do you know?
So this is basically by looking at how the pressure gradient affects the boundary layer, right? So essentially, if the pressure gradient has been adverse, then if you look at the evolution of the boundary layer over a region, you're going to see that without viscous effects, the shape factor would keep increasing, and viscous effects actually pulls back the shape factor, pulls back the boundary layer more and more towards the Blasius profile. So if you have 0 pressure gradient for a while, the boundary layer is going to come back to the Blasius boundary layer, right? But if you have favorable or adverse pressure gradient, it's going to make the boundary layer go one way or another. All right. Okay, and another thing is looking at the boundary layer, right? The black boundary layer is close to flow separation. Okay, now this is actually a good profile to look at what might prevent flow separation from happening. Now, if you look at this region, right, where the flow starts to become negative in velocity, and imagine this boundary layer is subject to a continuous adverse pressure gradient, right? So what are the forces if you just zoom into the layer of fluid that is becoming slightly negative or almost a 0 velocity? What force is causing this layer of flow to move downstream? What force is causing the layer of fluid to move upstream, to further become more negative? Right, so another way to say it is, if you have a layer of fluid that is on the verge of separation, what prevents it from separation by accelerating it forward? What would promote it to separate by pushing it backwards? Again, the forces affecting boundary layer are pressure force and viscous force, right? Does pressure force want to make you separate or not separate? Which direction is the pressure force? Upstream, right? The pressure force in the adverse pressure gradient always wants to make the flow separate. How about viscous force? If you look at the profile, right, think about what we have looked at in terms of the flow between two plates, right? What is how do you analyze what viscous force is forcing on this small layer? Right. Remember, like the plates examples we did, right? How do you compute the viscous force acting on this layer? Right. First of all, unlike pressure force is a body force, right? And how about viscous force? Is it acting throughout the body, like, or it is acting just on the surface? Just on the surface, right? So if you pick a layer, there are two surfaces, one below, one above, right? How do you compute the force on that layer, on that surface? It's viscosity times velocity gradient, right? And now look at the black line. The velocity gradient, first look at the velocity gradient at the wall, right? As opposed to the rest of the lines, the velocity gradient on the wall is of an opposite sign, right? So that means instead of the wall dragging the flow backwards, with the black profile, the wall is actually dragging the flow forward, right? Agreed? Now, how about over here at 0.1? The velocity gradient now is opposite from from y equal to 0, right? Which means the viscous force now switches sign. At the bottom of the wall drags the flow forward. At y equal to 0.1, the flow underneath y equal to 0.1 drags the flow above y equal to 0.1, drags it backwards, right? Which means the flow above y equal to 0.1 drags the flow below y.1 forward. Agreed? So both at y equal to 0 and y equal to 0.1, the flow sandwiched in between these layers are dragged forward by viscous forces. This is actually always the case as long as you have a curvature of the fluid like that, right? As long as you have a curvature, that's opposite of what we see in the like in the pressure-driven channel flow case. In the pressure-driven channel flow case, the profile is like that, right? The curvature is like this. So as long as we have an opposite curvature, like what we have over here, the viscous force actually drags the flow forward. When the profile has a curvature like that, the viscous force drags the flow backwards, right? As in the pipe and, so you're gonna do the piping in homework, right? As in the pipe and the channel case, like a curvature, a negative curvature, viscous force drags the flow backwards. A positive curvature, the viscous force drags the flow forward. So over this region, viscous force and the pressure force work in opposite ways. Pressure force wants the flow to separate. Viscous force prevents the flow to separate. So if you don't want flow separation, you want more viscous forces, right? So this is why in a thin boundary layer, there are more viscous forces if you're non-dimensional. So yeah. So in let me say, like in a lower Reynolds-Steinberg boundary layer, right? Lower Reynolds-Steinberg means viscous force is larger in comparison to other forces, right? Boundary layer is less prone to separation. And also in a turbulent boundary layer, right? There are more equivalence of viscosity by the turbulence that also prevents flow from separation. So if you want to prevent flow separation, viscous force is actually a good thing. All right. Okay, so let's actually start to look at some of the let's actually skip this. Look at how to design a high lift airfoil. So there are two different airfoils, and the envisage the pressure distribution on these two airfoils. And one of them is designed to be high lift in laminar flow, right? Working at the low Reynolds-Steinberg. The other is designed to be high lift at high Reynolds-Steinberg, where part of the flow is turbulent. Which one is which? Which one is designed to operate at to be high lift at laminar boundary layers? Which one is designed to be high lift at laminar then turbulent boundary layers? Take a guess. Okay, the answer is this one is high Reynolds number airfoil. This one is low Reynolds number airfoil. All right. You see over here, the airfoil, like for the secret of achieving high lift is preventing flow separation over the majority of the airfoil, right? If flow separation over here is fine, but you don't want flow separation over here or over here or over here, okay? And for laminar boundary layer, when the boundary layer is still relatively thin, you are having can afford to have a higher adverse pressure gradient. But as the boundary layer becomes thicker and thicker, there are less viscous forces, right? And you cannot afford to have a high adverse pressure gradient anymore. That's why the pressure gradient eases to almost zero along the trailing edge. And here, over here, it's designed to separate over here, right? That's basically trading drag due to separation over this region for additional lift, right? There is a pressure difference all the way to the trailing edge. Well, for the high Reynolds number case, right, the flow is going to transition somewhere over here. That is why in the laminar portion, right, you have the same trend. Initially, when the flow boundary layer is very thin, you can afford to have high pressure gradient. And as the boundary layer becomes thicker and thicker, you can afford to have less and less adverse pressure gradient. That's why you ease the pressure gradient over here. Up to a point where you are sure the boundary layer has transitioned into turbulent boundary layer. Then, like, you make it steeper again, right? Because you know the turbulent boundary layer won't separate as easily. You have more equivalent of viscous forces. But again, like, you need to ease it as you go towards the trailing edge, because again, as the turbulence boundary layer becomes thicker and thicker, still, even though there is turbulence, it's still easier to separate as it gets thicker, right? But you won't need as shallow of a gradient as in the laminar boundary layer. Okay, so this is so basically by looking at the implicit pressure distribution, you can already design good high lift airfoils that prevents flow separation based on what we know about boundary layers. All right. So this is almost the entirety of our viscous flow section. Next lecture, I'm going to mention a little bit about the three-dimensional boundary layers and start to get into compressible flows. Okay. All right, so see you in the office hour or on Wednesday.